welcome to video 8. This is Burke, and we're doing states of matter. Also, I have with me, this is Mac. His name is, I like to call him Big Mac. He's named after Macintosh, the apple. So he's going to help me today. I'm sure you're very familiar with the first three, and those are solid, liquid, and gas. Now, the next one you may have heard of is plasma, and we'll get into that a little bit. And then, okay, see you later, Mac. And then the last one is BoseEinstein condensate. And that one, I just want you to know that it exists. We're not going to delve into that too much. So here we go. Hope you're ready. So solid. Solids have what we call a definite shape. And by definite, we mean that it doesn't change in any way. Meaning that if you were to pick up a pen and put it in a different container, that's not going to take the shape of the container. It's not going to fill out in any way. It also has a definite volume, also meaning that it doesn't change depending on what you put it in. Now, the molecules that I'm showing you here in this picture are what we like to call tightly packed. Another way to think of it is as fixed, and you might want to write down that word, fixed. So let's go into a liquid. So we're going to start seeing how things change here. Now, liquids have no definite shape, right? Because they take the shape of the container, whatever you have them in. So if you pour them in a small glass, they'll take the shape of the small glass. If you pour them in a big bowl, they'll take the shape of the big bowl. Notice here the double lines next to it. It's trying to show you that there is some motion going on here. How we describe that motion or that molecular motion is we call it free-flowing. Another way to think of it is they're slipping past one another, sort of moving over one another on top and on top. Let's go to gas. Gas has no definite shape at all. It totally takes the shape of its container. It goes random, everywhere, everywhere, everywhere. A lot of people like to think of it in the motion of popcorn, just sort of ping, ping, ping after all the walls. You certainly can put gases under pressure. They certainly are. It lets you get more in the tank or whatever it is that you have. But what's very important here is that it has no definite shape, no definite volume, and that what we call their molecular motion that you see up here is what's called a random arrangement. And notice that there's arrows everywhere showing you how it's just pinging off the walls, all different shapes. So it's just random. So let's get into plasma, and this might be the first time that you guys have heard about plasma. Plasma is what we call an ionized gas. Now don't get too worried about those words. All it means is that it has pluses and minuses. So it has charges, and what they do is this occurs for us here on Earth in flames, so in fire, and in lightning is actually a great example of it. So whenever you are looking for molecular motion and things in plasma, the way to identify it is always look for those plus and minuses that you see there in the box. That's how you're going to differentiate it between that and a gas. Where do you find plasma in the universe? So this is a great picture of a galaxy from NASA. You find it in stars and the sun. Matter exists as plasma out in outer space, and that's really because of the very high temperatures when you're talking about stars and suns and things. So plasma versus gas, and I wanted to really write this out for you. They are very similar in molecular motion. And that molecular motion is that random arrangement. And we talked about that being like popcorn, going every different way. And the differences, remember, here are the charges or the particles that have pluses and minuses. And remember, those fancy terms for those are ions or electrons. Here's the one I told you. I just want you to know it exists, nothing more than in its name by itself. So the Bose-Einstein condensate. You may have heard it from the Big Bang Theory. They actually reference that from time to time. It forms from matter that is cooled. So a lot of people like to think of plasma as the really high temperature one, and the Bose-Einstein condensate is the cold one. So this is lab conditions only. You'll not find these on Earth anywhere. You'll not be out walking in the woods and just stumble upon them.
In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. This Bose-Einstein condensate is very difficult to imagine or to visualize.
So molecular motion, let's get into that. That's going to be a huge part of what you guys need to understand and be able to do and identify for me. So while I'm talking, I want you guys looking at the three pictures that you have up here. So solid, right up here. So we're showing you here that it's tightly packed, formed all the way. So if you put it in a different container, it's not going to change in any way. Again, look at the liquid. Look at the double lines that you see there. Again, it's trying to show you that it's flowing over one another, and we call those free-flowing. And then again on the end with gas, sometimes you'll see the multiple lines. Sometimes you'll also see the arrows there. And the gas here is a random arrangement. You guys have to be able to identify these pictures and be able to tell me the molecular motion. The other good thing that you're seeing here is that the adding of the energy and the removing of the energy. I just finished writing your task. There's two good questions on this, and it has to do with when you add energy, what motion and what state of matter do you go to? Okay, so make sure that you are comfortable looking and identifying this graph chart.
Here is summary time. Make sure you can describe each state. Make sure you can diagram it as well. Make sure you use the words shape and volume. And the two options you have there are definite and indefinite. And I've got 3 examples for you here. I would include plasma in your diagrams, but you don't have to include the Bose-Einstein condensate. As always, thanks for watching. See you guys in class.